All right. Okay, so there will be a there's a quiz today from 3 to 3:10, and there's in some cases some extra minutes added on. So from 3 to 3:15, we're going to be in quiz mode. Some of you, yeah, don't worry too much about whether you are in the undergrad or graduate. There's some settings are slightly different, but the quiz is the same. Can everyone just log on to Quirkus to make sure they have access to this quiz? And if there's someone who does not have access to the quiz, could you send a chat? Someone in the chat is asking if we are allowed to use the conclusion from question 1 in later questions. I don't really know why you would want to do that. Question 1 is important. You need to basically understand question 1 if you want to complete this class. Like, there's no way around it. Question 1 is essential. So, if you wanted me to give an answer, to be honest with you, I don't care what you use at all. However, for your own benefit, you should use it. Yeah, you should not use it. You should actually prove it. So that's what you should do for your own education. Hopefully that answers your question. Okay, so no one is having trouble with Quirkus? Okay, so someone should remind me in case I start eating into the 3 o'clock time. We should stop class at 3 o'clock for 15 minutes. Okay. And it's just it's a multiple choice. It's a multiple choice quiz, so should not be too time consuming. Okay, so we have a few things going on, which this week I hope we'll kind of finish some of them. At least the part of the course which is dealing with these qubit systems and tensor products and so on, that should be dealt with, by the end of this assignment. But I do want to just go through one example of a quantum circuit, which is maybe the most famous initial one that people realized could be made, that will save you work compared to a classical computer. So I'll do that. But also today, I wanted to start talking about SU2 and SU3. Sorry, SU2 and SO3. So I'm just going to spend a few minutes on quantum circuits, and then I'm going to move on to continuing our group representations. The idea here is that, and we also have the particle on the circle. So I want to say something about the particle on the circle. What I'm aiming at is just trying to get to more examples. So we need the representation theory of SU2 and SO3. We need the SU2 and SO3 representations. Okay, that will be very important for understanding the hydrogen atom and other things. Okay, the particle on S1, there's a few things that we need to cover about this, because the next example after that is a particle on R, And this is the traditional Schrodinger equation, the Schrodinger model with potential. And inside here is the very famous example, which we have to do next week, which is the harmonic oscillator, the simple harmonic oscillator. So we need that for these, and that's also, this hydrogen atom example is also the reason why assignment 3 is about Hilbert spaces, so that you'll be more comfortable with Hilbert spaces in this case. So anyway, that's what I'm aiming towards. But let's start with a really simple quantum circuit. So this is called Deutsch's algorithm. Okay. So suppose, so again, what computers are always doing is they're always dealing with binary numbers and binary functions that send a string of ones and zeros to another such string. And let's consider such a thing. Let's look at the simplest possible thing. Let's say we have a function given from 0, 1 to 0, 1. So there are 4 possible functions. This one, this one, this one, and this one. And notice that, well, this one here is what we normally call the constant function. And these ones here, this one here is not the constant function, but it is what we call a balanced function. Takes the same number of zeros and 1 values. And the other 2 functions are neither constant nor balanced. So let's just focus our attention on only constant and balanced functions. So we're going to exclude these. We're going to consider only these 2 possible types of functions. So if I gave you a function f, okay, and if you had to determine, and if I told you, so given, so here's the question. The question is, given the initial data of such a function, which is either constant or balanced, okay, and I'm assuming that these are exclusive categories. Really, you should probably think of the constant function as just one example of the balanced case, but never mind. We're going to consider balanced to be just this function and constant to be that function. So in the assignment, there's some discussion of this in a more complicated case, but I'm going to try to boil it down to the essence. So given a function which is either constant or balanced, determine which it is. Okay, so this is a kind of a weird type of problem to solve, but whether a problem like this is weird or not is irrelevant, because you might be able to take a problem and convert it into a problem like this. So you might, the determination of a price of a stock, let's say, you might be able to boil that question down to determining whether some function is balanced or constant eventually by some mathematical manipulations. So if you can have an algorithm that solves this problem, it might be useful to solve many other things. Okay, so don't worry about the particular nature of the particular format of the problem. It's clear that you're being given data in two possible classes, and you have to classify it. So it's a classification problem.
Can I just ask one quick question?
Yeah.
Why is that a constant function? That when you highlighted it, looks like the identity, if I'm understanding the notation properly. Like I would have thought 1 and 3 are the constant.
Oh,
functions.
I'm sorry. Yeah, sorry. What am I talking about?
Okay.
Yeah, I'm sorry. Yep, sorry. I am. I had too much coffee or something. Excuse me. Okay, rewind, delete. Let's start again. I felt like something was wrong, but I wasn't sure where I was going wrong. Okay. Okay. Good morning, everyone. Yeah, that's even wrong. Good afternoon. So thank you. So this is a constant function. As you can see, both values are 0. This is a constant function. Both values are 1. And these other ones are balanced. They have the same number of zeros and ones. So we have two classes of function. The problem that I was getting stuck on was that in higher dimension, so if this was a function from 0, 1 to the m, if it was a function from, let's say, 0, 1 to the n to 0, 1, right, then some of these functions would be constant, meaning that they would have a constant value. Some of these functions would be balanced, having the same number of 0 and 1 values, but a lot of them would be neither. A lot of them would be basically like a function that would take, that would look like, yeah, you can see what I mean, that that there are plenty of functions that are neither constant nor balanced when you're working on a larger domain. But in this case, we have two balanced functions and two constant functions, and we need to determine which is which. Okay, so if I gave you such a function and you had to determine which is which, then what would you do? Well, what I would normally do, so in the classical answer, so the classical answer would be evaluate. First, apply f to 0. And once we know the value of f of 0, we still don't know the answer to the question. So we've evaluated the function once. We did a whole bunch of work. The function is some kind of machine. We used up some kind of energy in order to run the machine, and we had to run it once, and we're still not done, so we need to run it again. So the second step is to evaluate f1. And if f0 is equal to f1, then it's constant. If it's not, then it's balanced. So we're done. So we need two evaluations. And those evaluations, you should think of them as, it's some kind of encapsulation of some longer computation, the nature of which you don't really know. But in whatever it is, you have to do it twice. Okay. So the quantum answer is different. So the quantum answer is that we're going to set up a quantum circuit, and we're going to evaluate once. We're going to run the circuit once.
Sorry, I don't think we see the circuit.
I don't know. Okay. So we're going to set up a quantum circuit, and we're going to evaluate once. Okay. So this is supposed to just give some kind of evidence that there's some kind of saving. There's some kind of savings that you get by using the quantum circuit. So my purpose here is not to talk about computation, quantum computability, or computational efficiency, or anything like that. I just want to demonstrate, what the basic principle is that this thing runs on. Okay, so let's take a look at the circuit. So the circuit involves this Hadam. It's a two qubit circuit, and it uses the function. It encodes the function in a unitary operator like this. So it's a controlled application of a unitary operator after the application of this H. So when you look at a circuit like this, you read it from left to right. The initial number of strands tells you how many copies of C2 are being tensored together. So this means that we have a 2-qubit system. Okay. Given a state of the system, which is a vector in the vector space on the left, okay, then we're going to read the diagram as a sequence of unitary operators, which is given by the vertical slices. So if you slice vertically, you see here that from C2 tensor C2 to C2 tensor C2, we have so H is 1 over square root 2, 1, 1, 1 minus 1. That's the Hadamard gate. Okay. And when we see that the Hadamard gate is being applied only to one strand, and nothing is being applied to the bottom strand, that means that what we're doing is taking the tensor product. This is the unitary operator. H tensor 1. Okay, then the next step, and there's another one of these here at the end. Okay, so this means that we have C2 tensor C2. We have H tensor 1. This is in more standard mathematical notation. Okay, and then we have this unitary operator UF, which I described before. So this UF, remember how it works. It's just a unitary lifting or a unitary embellishment or promotion of the original function, but it's done in a controlled way. So if I have x, y, I'm going to write it the way physicists do, and then I'll explain. This goes to x, y plus f of x. Okay, so what does this mean? This means that x tensor y, the decomposable vector in C2 tensor C2 is going to be sent to another decomposable vector, x tensor y plus f of x. Okay, where here x and y can be 0 or 1, and this is the standard basis for C2. You could take this to be, for example, 1, 1, 0, and this to be 0, 1, if you wish. Okay, so this is, again, remember, why is this a unitary operator? The reason is because this is an orthonormal basis. It has norm 1 and they're orthogonal to each other. They each have norm 1 and they're orthogonal to each other. And this operator, I'm defining it on a basis. And if you can, and you can see that here I'm taking the tensor product of two unit vectors, and this will be a unit vector. Okay, because remember that the inner product on V1 tensor V2, the inner product on V1 tensor V2 is always defined to be is defined such that U tensor V W tensor Y is really, or let me put it as U1 V1 U2 V2 in U tensor V, okay, is defined as the product, where you take the U1 U2 inner product in U and multiply that complex number by the V1 V2 inner product in V. Okay, so when I take the tensor product of two unit vectors, then when I take this inner product norm of this new vector, I'm going to get exactly just 1 times 1. And so this will be a unit vector. So this ranges over all the unit vectors of U tensor V. And I explain what this operator does to each of these unit vectors. It takes it to a vector like this. And this is another unit vector, because what's inside here, this is one of the unit vectors, and this quantity, this is a sum in Z mod 2Z. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. Okay, so that means that I'm basically telling you that this unit vector gets sent to this unit vector. And so if this is a transformation that it takes unit vectors to unit vectors, and which is, which takes, it's basically a bijection on, it's a bijection on the orthonormal basis. This is a bijection on the orthonormal basis. This means that we get a unitary operator. It's a very special kind of unitary operator. I mean, you could imagine, like any rotation, for example, is a unitary operator, but a rotation doesn't send the basis to the basis. Even if you rotate by 90 degrees, it will take one basis element to the next, but it will take that basis vector to minus the other one. And this is a very special unitary, which actually takes the basis exactly to itself. Okay, so we have this other unitary operator, which we called U sub F. And so this circuit is being expressed as a composition of unitary operators acting on a tensor product of C2 with itself. That's what a quantum circuit is. So let me continue this diagram. This goes to C2, tensor C2. The first copy is the control. The second is where the function is acting. And then finally, we have another Hadamard tensor 1 into C2, tensor C2. So this composition, this is the algorithm. This is the quantum algorithm, or the quantum program or circuit, the quantum circuit. Which replaces F in the classical case. So what we're going to do is treat this thing, this gadget, as being our given data. What data is being used in order to build this thing? There's only one non-trivial piece of information that we need to build this circuit, and that is the function F, which is exactly the same data that we needed, that we were given in this problem. So given this function, F, okay, we can either just take it as a little machine and we can evaluate it, or we can embed it into a quantum circuit and produce this, and then try to evaluate this. And the difference is going to be that this circuit only needs to run once, and it will give us the answer. Is the conceptual picture clear? what what I'm trying to explain? So we would like to see now, we want to show that F can be classified after only one run of the circuit. Okay, so let's see how that works. Let's take the circuit and maybe to emphasize, I'll put UF here. Okay, and the idea is, so remember that there was this interesting phenomenon, I covered it a little bit at the end of last class, that that with these unitary, so okay, what's the basic idea? The basic idea is actually not that difficult to understand. It's that, you know, what does a usual classical function do? It says, you know, you give me an input, I will give you the exact output. You know, and so there's two possible inputs. So if you want to know the outputs, you've just got to plug in the possible inputs, and then you'll know what the function does. But the thing that's happening in quantum mechanics is that these inputs, they're like a series of switches, right? So if you want to plug in the value 0, then you should switch your light switch down, and the function will look at that and will give you an answer. And if you switch it up, then the function will give you a different result. But in quantum mechanics, you can have a superposition. You could have a linear combination of those two input states. So if you say, well, I don't want to feed you, you know, I don't want to feed you 0 and I don't want to feed you 1 because I want to know both answers. Basically, I want to know both answers simultaneously. So if you want to know both answers simultaneously, you've got to give both inputs simultaneously. And in quantum mechanics, that is possible. You can give them a superposition of inputs. So how do we do that? Well, that's the reason why this Hadamard is here, because you see how Hadamard works. Right? It takes a normal input, like a classical input. Let's say if I feed it 0 here, then 0 would be sent to 1 over square root 2 0 plus 1. Okay, so the purpose of this Hadamard is that it basically is taking a single, like a state which is an eigenstate of the observable, which tells you whether it's on or off, and it splits it into it creates a linear combination. It's basically like a rotation, which does the following. Right? It rotates. It's basically like a rotation that does this. So the purpose of the Hadamard thing is that it takes something which is classically on or off, and it rotates it by 45 degrees. Okay, and why is that useful? Well, the reason is because it's very easy to prepare these classical states 0, because you can just, you know, you can, if this is an electron coming in, electron has a spin property. That spin property is like a switch. It can be either up or down. There's many things that have that property. It's not important that it's an electron or that it's even spin, but the point is that it's a two-state system. So it's if you want to be sure that you're feeding the algorithm something that you know what you're feeding it, then the easiest way to do it is to just measure the electron. And if the electron is spin down, okay, then you know that it is in that state, and that's what you can provide the algorithm. Okay, but now if you want to do something fancy with that state, you need to move it into a superposition. Remember, this is not about, this has nothing to do with entanglement yet. So I just want it to be neither classically on or off. So I rotate it. Now it's kind of, it's a linear combination of on and off, and you feed that in as a control to this evaluation. And what should we feed into this thing? Well, let's see. Just to make the calculation a little bit faster, what I'll do is I'll feed in 0, -1 to this side. Okay, so how did we get this? Well, you could have used another Hadamard if you want. I'm not. You could have for example, done something like this and fed it 1. Okay, and then it would give 1 over square root 2 0 -1. Okay, but let me just ignore that and just say that we feed this in. This will be our input, fixed input. Okay, and then this is going to traverse the circuit, and we're going to get a unitary transformation. Oh, I'm sorry, let me make it even more clear. When I say this is the input, what I really mean is that the input is 0 tensor 0 -1. It is a decomposable state. In C2 tensor C2. Okay, so it is a tensor product of vectors, one in the first vector space and one in the second vector space. Okay, now this is going to pass through, and what we're going to end up with is some vector. The output is some vector in C2 tensor C2. And then what we're going to do is, I'm going to draw it with a red. Okay, we're going to measure here. Measure. At some point, there has to be a measurement. At the end of your circuit, there has to be a measurement. And you don't need to measure each wire of the circuit. You could measure all of them, or you could just pick one and measure it. And I'm just going to keep this simple. We're going to measure just one single point. And what that's going to do is we're going to, when I say measure, we're going to measure the on-off observable. The observable that has this, that has on and off as its eigenstates. Okay, so all we need to do now is compute a unitary matrix. So let me just do it in a kind of shorthand that they often use. So so let's go step by step. So 0 tensor 0 -1 is going to be sent by H tensor 1 to okay, I'm just drawing the tensor product vertically. It doesn't matter. Okay, and then I need to apply this controlled application of F. So, well, we saw what F does. So F doesn't change the first argument, but it changes the second. Now, and what does it do? It just changes it by adding the value of F. So, for example, let's say that we just look at UF applied to 0 tensor 0 -1. And you'll see why I'm using this 0 -1. It's just a trick that I'm using for the following reason. So if I do this, so this is the same thing as UF applied to 0 tensor 0 minus 0 tensor 1. Okay, and remember how this works. This is going to be unchanged on the first, but the second will be 0 plus f of 0. And therefore, this is just f of 0. And then I'll get a minus with 0 tensor f of 0, 1 plus f of 0. Is everyone okay with this intermediate calculation? Let me know if there's a problem. Now, what is f of 0? Well, f of 0 is either 0 or 1. Now, if it is 0, so if f of 0 is equal to 0, then that means that this thing is not changed at all, right? So this would be equal to 0 tensor 0 minus 0 tensor 1, which is exactly the same as what we started with. Okay, if f of 0 is equal to 1, however, then we're going to get 0 tensor 1 minus 0 tensor 0, which is exactly the negative so it's exactly the negative of this. Okay, that's the reason why I wanted to input 0 minus 1. It's just because I have arranged a linear combination so that if 0 and 1 are reversed, it creates a sign change in the wave function. Okay, so another way of writing this answer, which is a shorthand, is that we could say that it's just want to write it in a good way. We could write it like this, that it's minus 1 to the f of 0 tensored with the same input. Oh, sorry, I was switching my notation. Let me just put this normal configuration. Okay, so you see what I did? It's confusing because this controlled unitary does not affect the first argument, but because the combined effect is that it switches the sign of the second argument or not, depending on the value of f of 0. Okay, depending on the value of f of 0, it either switches the second argument or doesn't. And because this is a tensor product, that sign is valid for the entire thing. So that means that I can move the sign from one side to the other. That's an element of the field, so I can move it to the other side, and I have the sign here. So now it kind of looks like it doesn't actually have an effect on the second argument, but I mean, that's only because of the funny choice of the second argument. You see what I'm saying? Is that clear? So UF applied to this quantity is itself, but multiplied by a phase. And that phase is different depending on whether the function has value 0 or 1 on the first number, on 0. So this is very elementary, but it is confusing, and so I just wanted to do it in a kind of pedantic way. So, okay, now what would happen? So that was this term. That was the 0 tensor this term. That's one of the tensor. If you expand this tensor product out, one of the one of the summands will look like this. And what you see is that because 0 is the control bit, it's the value of f on 0 that is being used in the remainder of the calculation. Now, in the second, so if I had changed this to a 1, right, then what I would be doing is I would say, it says that I'm supposed to add to y the value of f on x, the value of f on the control. So this means that what would occur in this calculation would be f of 1. It would be exactly the same calculation, but this would be f of 1. And so what I would get is minus 1 to the f of 1. So in total, what we get is minus 1 to the f of 0 times 0 plus minus 1 to the f of 1 times 1 tensored with 0 minus 1. Almost as if it didn't affect the second argument. But you have to keep in mind, these are bilinear operations. Okay, and then there's a 1 over square root 2, which I forgot. Okay, so this is just a kind of shorthand way of doing this. So what we see, is just an observation, is that the classical values of the function f are encoded in phases of the states, of the quantum states. So what I mean is that it's a phase. It's a sign. It's a number like e to the I theta in front. It happens to be minus 1 or plus 1, but it's still a phase. So what you're starting to see is that you should think that this is 0 and 1 are like two classical. It's like the cat being dead and alive, or the cat being hungry or full. And what's happening here is that we're getting a combination of the two classical states, but with different phases. And what that should remind you of, it's like an interference pattern. It's like we're getting some of this state and some of that state with different phases. Okay, and finally, then we apply. Oops. And then finally, we apply the last Hadamard. And well, actually, let's not even bother with the last Hadamard. Let's even remove it. I'm going to measure right here instead. Okay, so if we now measure this, notice what happens. If f of 0 is equal to f of 1, that means that the phase of 0 and 1 are the same. They have the same phase. So we're going to get plus or minus 0 plus 1 is the result. Okay, and that plus or minus is an overall phase, and so it's not relevant. Okay. If f of 0 is not equal to f of 1, then this is going to give plus or minus 0 minus 1. Okay, so this means that we are getting two distinct states, right? Which exactly classify the function based upon phase. So this classifies the function. But there's a problem, but the problem is that the result is in a superposition. So it's a probabilistic result. So that means that if I measure, if the function happened to be balanced, if the function happened to be constant, then I would know that I'm going to get this state. And if you measure this, then you don't know whether it's going to be on or off. It's 50% probability. And if you measure this one, it's also 50% probability. So even if you repeat the experiment a million times, you're never going to know, you're never going to be able to classify because this result, even though the two states are different, the probabilistic results are the same. Okay, so now let's do a second measurement. Let's do the Hadamard. Let's say this is the second measurement. This was the first measurement. So the second measurement is going to take these states which are in this annoying. Why is it annoying? Why is the superposition annoying? The reason is because it is not aligned with the observable that you're making the measurement for. Because we know that the measurement is the thing that tells whether it's on or off, what we want to do is rotate these two resulting states back so that they are eigenstates of our observation. Right? So apply H again. Okay, and then 0 minus 1 would be sent to the difference of the two columns. The difference of the two columns would be remember that the Hadamard looks like 1, 1, 1, minus 1. So the difference between the two columns would be would be 1, a constant times 1. And the sum of the columns would be some constant times 0. And then now we're in business, because now we are actually back into the classical realm before we even make our measurement. So these, when measured, give a definite result. Right? If the function, so i.e., if f is constant, the result is 1. The result of this, sorry, I switched them. I'm sorry about that. Let me I swapped them by mistake. So if the result, if they were constant, if the function was constant, we would get 0 plus 1. 0 plus 1 would be sent to 0. And then we would measure 0. We would measure that the switch is off with 100% certainty. I mean, in principle, if you had perfect equipment. And if f is balanced, the result is 1. So we get a determination, we get a complete classification in only one run. Okay, so Deutsch was one of the early pioneers in this quantum computing, and with this idea, with this simple idea, he kind of opened up the entire field. this simple algorithm, as simple as it is, it holds the key to what you can do with quantum algorithms. It's basically making use of making use of these interference patterns in order to make the answer just suddenly appear. So in a way, what the algorithm is doing is it's computing the values of f for all possible inputs, all at the same time. And it's arranging the result in such a way that when you make your measurement, you're getting the information that you need. So okay, so anyway, that's that. In about a minute, the test will become available. So, so go ahead. I'll be back at 3:15. If you have any questions, private message me on the chat, but don't use the chat during the test. And there's extra time just in case there's some kind of technical failure. So I just put a bit of extra time. So, you know. Okay. Okay, any questions or can I move on to some representation theory? Okay.
Sorry, I actually did have a question.
Yeah.
The first quiz, the grade was never like actually showed up on Quarkus. I know we went over what the answers were, but I was just wondering like if just in case I forget what I answered by the end of the term and I want to know like where I might stand in the course.
It should appear in Quarkus at some point. Maybe I didn't click on the right thing. I thought it was already there. I'll check it out.
Okay, yeah, thanks.
Any other questions? Okay. Okay. So okay, so let's talk about let's go back to representations. For U1, SU2, and SO3. Those are the key ones for us for the time being. So we saw, let's just review for U1, any representation let's say finite dimensional representation, complex representation, is a sum of irreducibles, and the irreducibles are parametrized by an integer. So any finite dimensional complex representation decomposes let's say V is VQ1, VQN. For integers, Q1, Qn. And can be written, and the action of e to the I theta on V is a matrix, a big n by n n by n matrix. And we can express that as e to the I q theta, where q is the charge operator, which is just these numbers on the diagonal and zeros elsewhere. So the way that rotation by theta acts on here is that it acts at a different speed on each one of these factors. And the speed of rotation is what we call the charge. And the charge can be any integer, and so we have a matrix of charges, a charge matrix. And so notice that what is happening here, notice that this is an example of Q being an observable. In other words, it's self-adjoint, right? And then that is becoming, that becomes like, you multiply by I, okay? Then this becomes skew adjoint. And that means that it's in what we call UN, or the Lie algebra of the unitary group. And then we exponentiate this for a certain amount of time, or what we normally call theta angle, because since this is an action of, and this is an action of the circle. Theta is, we're thinking of theta as being in the real line where, or you could think of theta as being, in the real line mod 2 pi z. So it's periodic. 2 pi e to the I theta is periodic with period 2 pi. And then we exponentiate this thing and we get a unitary operator. So this is an example of the standard yoga, where you take a self-adjoint operator that's an observable. It has real eigenvalues. In this case, it's not just real, but even integer. Then you multiply by I, you get something skew adjoint. You exponentiate, you get a unitary. Then the unitary gives a symmetry of the system, or a time evolution, or whatever, however you want to interpret it. It gives you a unitary transformation of the Hilbert space. So when we talk about charge, I just want to make a comment. Normally we talk about charge as something that is conserved. Okay. So what does it mean when we say that? So what does it mean when someone says charge is conserved? Okay, so when they mean that charge is conserved, like mass, is conserved, or energy is conserved, or electric charge is conserved, what it means is that in time, in the evolution of the system, charge doesn't change. But the evolution of the system is given by a different observable. It's given by not the charge observable, but the Hamiltonian. So if a state has charge Q at time t0, then it should not change. It should be Q at time t. So in other words, the time evolution should preserve the charge. So in other words, that if we evolve psi of 0 to e to the minus I t h, this is the Hamiltonian now, psi of 0. So this is the time evolution, Schrodinger time evolution. Then Q should be should commute with the action of the Hamiltonian. If the charge operator commutes with this unitary time evolution, that means that that means that in a way the charge operator does not see the Hamiltonian. The charge operator has certain eigenspaces, and it has certain eigenvalues, and the Hamiltonian should preserve those eigenspaces, and it should preserve those should commute with the charge operator. So this would imply that charge is conserved. The fact that these commute would imply this. Okay, so so the lemma is that so if the charge commutes with the Hamiltonian, okay, then charge is conserved. So I just want to point out a couple of things. This is exactly how physicists would phrase it. They would talk about the commutator between Q and H. But mathematically speaking, this is a bad operation to do because this is self-adjoint, this is self-adjoint, but this bracket is not self-adjoint. So this is not the Lie bracket on the Lie algebra. Really, this is another way of saying that IQ and IH, when we take the bracket between these, this is in UN, this is in UN in the Lie algebra, and this is in UN. So we require that this is 0 in UN. That's the meaning of this condition, so that the infinitesimal symmetries determined by these two operators, they should commute. So if this is the case, okay, then e to the q will commute with the exponential of e to the minus iht. You could see that in one way, just in terms of the power series that determines this. The power series will have powers of h. H commutes with q, so you could just take q through the entire power series. If you wanted a better argument, there's a there's a good lemma. So this proves the result. That's really the important thing to know, that to really call something a charge which is conserved. I mean, you could in principle call any observable a charge, really, if you wanted to. But when they give it the name charge, it's typically because it is conserved. At least they think it's conserved in some situations. And that would mean that it commutes with the Hamiltonian. So you can simultaneously diagonalize them. And in particular, what it would mean is that those numbers, those charges, they would have a classical meaning, because the charge has a well-defined value yeah. So there's another lemma which is related to this, which is good to know, a more general fact. So let me just give some definitions. So if we have a matrix, and let's assume that we're in matrices, just to avoid talking too formally about Lie algebras and Lie groups. Let's say that we have matrices, and let's say we have, so any matrix defines an operator on matrices, which is called the adjoint operator, little add x, lowercase add x, this is the so-called adjoint operator, the adjoint action of x on matrices. Okay, and it's kind of silly. The adjoint action of x on y is exactly the bracket of x and y, which means the commutator, xy minus yx. So this is defined for any element of a Lie algebra. Any element of a Lie algebra, you can of course bracket it against the rest of the Lie algebra, and that will define a linear operator from the Lie algebra to itself. So if x is in a Lie algebra, then add x is a map from the Lie algebra to itself, a linear map from the Lie algebra to itself. And on the other hand, number 2, there is, so if G is an invertible matrix, defines an operator which is called uppercase add G on matrices. And this one acts on a matrix by conjugation. So you need that G is invertible in order for this to make sense. So this is called the adjoint or conjugation action of a Lie group on its Lie algebra. Okay, and there's a nice lemma which relates these two. So this is a lemma which relates it's saying that big add is related to little add via the exponential map. What does this mean? If I write it in a formula, it means the following. If I take G to be the exponential of a matrix X, that way it's for sure invertible. Then if I conjugate by G, this will be the same thing as the exponential of the little add action of X on Y. So written out, if I write this out, oh, and maybe I should have written this. Yeah, sorry. Instead of this, I'll just write it as big add of G on Y, like this. And then you could really remove the Y from this. It's just an identity of operators. So in other words, if I write this out just as removing all language from it, it's just a formula like this. E to the x, y, e to the minus x is equal to the exponential of add x applied to y, which means if I expand this out, it's going to be the exponential of bracketing x against y. So the first term would be, I'll just write it out as an infinite sum. So the first term would be just the identity. So it just leaves y alone. The next one is going to be x commutator y. The next one is going to be 1 over 2 factorial x y, and so on. Okay, so you can compute the left-hand side by using the right-hand side. It's basically just an identity. But the cool thing is that the right-hand side makes sense in any Lie algebra. Whereas here, yeah, this is really a Lie group element, which I'm using to act on the Lie algebra. Anyway, I think I made it clear what the statement is. Okay, suppose we want to prove this. An easy way to prove it would be to introduce a parameter and to use calculus. So or to use differential equations. So we'll introduce a parameter, t, and we'll define g. So in the exponential. So we'll try to prove e to the tx y e to the minus tx is equal to exponential of t add x applied to y. So we're going to prove this. So for t is equal to 0, it's obviously true. So it's true at t equals 0. Great. So we're halfway home. The other thing is that this is a path of matrices. To show the paths, the left-hand side and the right-hand side are the same paths of matrices. Let's compute the derivatives. So if you compute the left-hand side derivative, what are you going to get? Well, you'll take down an x, and then there's going to be a second term, which will be e to the tx y x e to the minus tx. Is that okay so far? I hope I didn't make a mistake. There's two occurrences of t, so there's two terms. And then if I write this, okay, and then here we look, if we look here, this is e to the tx, and this is x. These two will automatically commute, because this is just a bunch of, actually, you could even prove that using the same idea, using the same differential equation. You could take the commutator between them. That would be a path of matrices, which at t equals 0 is just 0. And you could prove that these two commute by using this type of argument. But never mind, I'm claiming that it's obvious that they commute because of the power series. So this is the same thing as e to the tx xy e to the minus tx minus e to the tx. Well, then I can combine them. And therefore, I see that I get an e to the tx commutator e to the minus tx. And this is the add of tx, the add of e to the tx on the commutator xy. Sorry, let me fix this. So this. Okay, yeah. Let me back up a little bit. I was going in a direction that I don't want to go in. Let me, just to make this clearer, I'm going to put the left-hand side in here. Oops. Okay, so I'm taking the derivative, and I get this. Notice that this quantity occurs here. It almost occurs here, except for the fact that I have these two. So what I'd like to do is to switch their order, which I can do for the same reason I just mentioned. So this will be x minus does that make sense? And therefore, this is the commutator of x and e to the tx, y, e to the minus tx. So in other words, by introducing this parameter, what we have is a path of matrices. And it satisfies the condition that P dot is equal to little add x applied to P. And P at 0 is equal to y. Okay, so this path, because of the way it's constructed by by putting t into the argument to the exponential, this thing satisfies a differential equation. It's a differential equation on matrices, saying that the derivative of the matrix is the commutator of x with that matrix. Okay, and so if we compare that with the right-hand side, but the right-hand side is just exponential of t add x applied to y. So its derivative is just add x. So if this was p tilde, this would be p tilde dot is equal to add x applied to p tilde, because it is literally the exponential of this operator. And so when I differentiate with respect to t, that's just going to bring this operator down in front. Okay, and p tilde at 0 is obviously just y. So they coincide. They satisfy the same differential equation, same ODE, with the same initial condition. Okay, so we have this this expression, which is kind of useful. It's somehow relating. I don't like that. It's somehow relating. A group computation, which is happening on the left-hand side, with a Lie algebra computation, which is happening on the right. Okay, and so you can kind of see that. Okay, so how is this used? Well, you know, the point is just that. So the application of this, the obvious application, okay, is that if Q is some observable, right? This is how physicists sometimes think that they, you know, if you are, if you're working with a quantum system which has a certain Hamiltonian and you have this other observable that you're interested in, it could be position, momentum, what have you, right? Then you might say, well, how is position affected with the passage of time? How does position vary with time in this system? Okay, but the question is incomplete because you always have to answer the position of which state, right? So you usually have to have a state and you let that state evolve, and then you measure the position, or you see whether the state is in an eigenspace of position. But oftentimes you want to study the system without specifying its state. So if we don't want to say exactly which state we happen to be in, but we just want to know something general about how position operate, like this observable Q varies with time, what you could do is you could take the time flow operator, we construct the unitary evolution operator, U of t, which is just the exponential of t times h. So this is in UN, some unitary matrix, okay? And by the way, this is called the propagator. Because it propagates your states forward in time, okay? And you basically say that, well, okay, if I wanted to study how this observable behaved with respect to time on a state psi, what I would do is I would take that state psi, I would apply u of t to psi at 0, right? That would give me psi of t. Then I would apply q to this and I would ask some question about it. For example, you might ask, is it in an eigenstate at time t, right? This would be saying that at time t, psi of naught lands in an eigenstate of q. Okay, that would be a typical thing that you might want to know. But you can see here that this doesn't really require the knowledge of psi naught, because you could just say that q u of t, sorry, it doesn't necessarily require the understanding of the state evolution in time, because you could just conjugate by u of t, and this would give q psi naught. So the way that physicists think about this is that they say, well, instead of following and flowing, propagating the state as a function of time, their idea is to forget about the state, the particular state evolution psi of t. Instead, view the operators, the other observables, q, as varying, so that q of t is like u of t inverse q u of t. Or in other words, it's big add u of t applied, well, I'll put the inverse on the other side, it's just because of the way I set it up, applied to q. Okay, so this is what's called the Heisenberg picture, as opposed to the Schrodinger picture, which is the standard picture. What is a picture? Well, I mean, it's just the idea of how you implement time evolution. Do you implement it as a unitary transformation of the state space, or do you implement it as a unitary transformation the adjoint action, the big adjoint action or conjugation on the algebra of observables, on the unitary group? Do you think of it as a change of all the observables? All the observables get conjugated with respect to U of t, or do you view it as a change of the states? Mathematically, there is no difference to this. It's a silly distinction to make, but anyway, it's a big thing in quantum mechanics. Is that clear? And anyway, this makes it more clear that a given observable is conserved. This is what is literally meant. So this makes it more clear. What is meant by an observable Q being conserved, i.e., it means that Q of t, if you define it to be the adjoint action of the propagator on Q of 0, okay, should be just equal to Q of 0. That the observable does not change in time. Okay, and this follows immediately from little add of h q equals 0. So if add h q, little add h q is equal to 0, i.e. h q commutator is 0, then this implies by the lemma that big add of exponential of h, or sorry, of minus I h bar q is equal to q. Oh, sorry, I'm going to move this to make it more legible. Big add of exponential of minus I h t applied to q is equal to q. So that, and just look at the lemma. The lemma is basically just saying that if your Hamiltonian adjoint action of the Hamiltonian with q is if add x y is 0, then the exponential of this adjoint action will also just be y. It'll just have the first term, the identity, and so the left hand side. This is the Heisenberg picture evolution of the operator y, right? And that is the exponential of the little add of the generator acting on y. The generator here would be the Hamiltonian, and if the Hamiltonian commutes with q, then the right hand side is just q. You have to get used to these things. It may look like a huge stream of information, but really there's only a small number of facts that you need to get straight in your head about the relationship between the Lie algebra and the Lie group. Any questions about this? This is the meaning of, like, what does it mean for an observable to be conserved? It means that it commutes with the Hamiltonian. Compare this with classical mechanics, where a function on the phase space would be fixed by the Hamiltonian flow exactly when it Poisson commutes with the Hamiltonian to be 0. Like when it Poisson commutes with the Hamiltonian, then the Hamiltonian flow fixes that function. Similarly here, an observable, if it commutes with the Hamiltonian, is fixed. Any questions about this? Okay, so next week we're going to do the representation theory of SU2. And the main thing that you should think about, prepare yourself in the following way. So think about the following. Okay, that it's about mirrors and rotations. And this, you can think of it in 3D, but actually in 2D, that's good enough for what I want to explain. So if you, in 2 dimensions, right, everyone knows how to rotate. You just rotate a certain angle, theta. Everything is rotated a certain angle, theta. Usual rotation. But there's a second operation, which is also an orthogonal. These are orthogonal transformations of R2. So there's another orthogonal transformation, which is not a rotation, and that is what you get by looking in a mirror. So there's a mirror, and whatever person you have gets reflected in the mirror. Okay, and this is obviously not a rotation because it changes the orientation. Okay, but if I reflect again, so let's say if I start here, number one, number two, I land here, and then if I reflect through the, sorry, this is not the best thing to reflect through. Would be a good one. Oh yeah, this is a good one. So this is reflection 1. That took me from here to here. And then reflection number 2 is going to take me to like that. Oh, that wasn't very good. Like that. 3. Okay. So by doing 2 reflections, I am orientation preserving again, and I have essentially accomplished a rotation. So 2 reflections is a rotation. 2 reflections is a rotation. Okay, and so I don't know why it's doing this. Okay, so from 1 to 3, we get a rotation. What is the angle by which this thing is rotated? So don't answer. My question is, what is the angle? Here's the puzzle question. What is the angle by which it is rotated? Number 1. And number 2, does this depend upon the position of the mirrors? Puzzle. Okay, think about it. Next week, we'll see the answer. Any quick questions? I'll stick around for 5 minutes or so.
I have a question.
Yeah.
The adjoint, like the small AD,
yeah,
that terminology like has very little or nothing to do with like the adjoint, like a star algebra or something like that kind of involution.
Well, we even saw before, we had this idea of self-adjoint.
Yeah, that's what I mean.
Different. Those
Yeah,
are different.
completely different. Yeah, okay.
Yeah, it's totally not, they're not the same.
I have a question about the quantum computer stuff from the first half.
Yeah.
Maybe it's more of a pragmatic question for an engineer or something, but how would you construct like the gates, right? Because to construct the thing for F, wouldn't you already need to have a description of how F acts to even build it in the first place?
Yes. Oh wow, everyone just left. Okay. I guess they
Didn't like
really
my
didn't
question.
the
Yeah.
So, so it's a very interesting question, and basically, you can ask the same exact question in the classical case, right? If you have a function that you love, like you worked all this, you did all this work to develop this mathematical function, and then someone asks you to implement it in a circuit, right? So what do you do? Well, the way you do it, in like the amazing thing about computation is that they figured out a basic set of gates, very simple gates, like a transistor, and they do simple logical operations like and, or, exclusive or, stuff like that. There's only there's a finite number of these very simple gates, logic gates. And then there's a theorem that is pretty easy to check, that with those, with that set of logic gates, and in fact, you can even reduce it to 2 or even 1 if you use NAND or something, I can't remember, you can obtain any Boolean function from a concatenation of those basic gates, okay? So basically you only need, in the classical case, you only need a couple of basic gates. And from that basic gate, you can produce any Boolean function. So the corresponding theorem for quantum computing would be something like any unitary operator can be obtained by a composition of things that come from a finite set of these gates. And that's not exactly true. It kind of depends. I mean, you might be able, and there are results of the type that you can get a dense set of unitary operators by composing these gates. There's also the additional problem or interesting feature that some of these gates will have parameters in them, like a continuous parameter. So that means that even though it's a simple gate, and even though it is physically buildable, physically realizable, it still might have like a very large parameter space. And so it might not be the exact analog of a classical gate, which is basically just a switch. Okay, so having said that, right, that you may not be able to get every possible unitary. The point is that you can get a huge number of unitaries which are sufficient for doing pretty much any calculation. And so then the idea is, then you get another step even better. So if you choose the gates properly, then you can do something like the following, where if you know what your classical function is and you know how to build it in terms of gates, then if you work it correctly, then you can just replace each classical gate, each tiny classical gate, with the quantum analog. And that will do the job of building this F in the quantum setting. So what I'm trying to say is that this idea of upgrading the function to a unitary, if you work it out correctly, and if you build the quantum gates in such a way that they're in correspondence with the classical gates, you might be able to do it by just upgrading each of the gates, and then the circuit diagram becomes the same. So it's a very beautiful kind of idea that all you need to do is quantize the elements, the tiny pieces of the circuit, and you don't have to worry about the whole circuit. The whole circuit is emergent something from the diagram. Okay, but then we're left with, how do you build the individual gates? How do we build the quantum individual gates? So, and these things are, okay, so the first thing that you need is, what are the wires? So the wires, they are supposed to be a two-dimensional quantum system. And there's many choices for that. One of them would be the spin of an electron. Okay, and another one would be the polarization of a photon. The polarization of a photon, even though the photon is spin 1, the one of its three, even though it's spin 1, it turns out that it can't have spin 0. just because it's massless. And so it ends up being a two-component entity. So it's basically behaves from a quantum mechanical point of view like a spin, like an electron, or like a one of these spin 1/2 particles. So you could use the polarization of a photon, which is even easier, right? Because you can just use mirrors and polarization filters, and you can use those things to build your gates, literally. So you can, for example, if you take a polarized beam splitter, right? You could take what does that mean? It means that you can put in. So there's crystals, for example, that will do this. You shine well, you put a photon through one of these beam splitting crystals, and it will split it into two paths, two physically different paths. And along one path, it will be circularly polarized in one eigenspace, and in the other, it will be in the complementary eigenspace. So there you go. You've got a Hadamard matrix. 0 is sent to 0 plus 1. That's how it works. Where the 0 and the 1 now become the circular polarization in the left-handed or right-handed formula. Or you could have linear polarization, or you could have both. You could put something which has linear polarization in to the crystal, right? And then it'll split it into circular left and right polarized. And then you have these beam, the combiners, and then you have the mirrors. So all of these optical apparatus, if it's done, with lasers so that everything is roughly in the same state, and if it's done clean, then you can set up a quantum computation with. That's why they do all these quantum teleportation experiments with lasers, because it's relatively easy to deal with them. But the point, the reason why it works is because we have physical entities, we have physical apparatus which can interact with the system which is in the wire, right? That mirror will interact with that polarization state. It's not just, it's not just, you see, like if the mirror only reflected, if it only changed the physical direction of the beam, and if it didn't do anything to the polarization state, that half silvered mirror, the beam splitter, right? It wouldn't be considered a quantum gate because it doesn't act on the polarization state. The position of the photon in space is not important. It's the polarization of the photon that is being acted upon as a quantum system. So you keep that photon on your bench somehow, right? And then you act on it by certain filters. And then you care about the polarization. You don't care about where the photon is. You're never going to be able to figure it out anyway, where the photon is. What you can measure is the polarization of the photon. And you can do that at any point in the beam. It doesn't really matter. So that's the type of experiments that they do. On the other hand, if you're going to use electron spin, then what you need is something that will interact with the spin state. And if there wasn't anything that interacted with the spin state, then we wouldn't know that the electron had spin. So we need to know, the reason that we know that electron has spin is because spin of a charged particle actually interacts with the magnetic field. It changes the way that it interacts with the magnetic field. And so that means that if you're going to use electrons, you need to use magnetic field. So now you're in magnets. You're a magnet person if you're going to do these experiments, because that's what your circuits are. Your circuits are magnetic fields. I mean, your circuit components are magnetic fields arranged in such a way that they will have influence the spin state, right? And again, the position of the electron is not important. It's really, did it interact with the magnetic field? What was the magnetic field, and so on. Anyway, that's what the assignment question is really secretly about. You've got this observable, which is acting on a two-dimensional state space. And that observable is made from the Pauli spin matrices, 3 of them. And therefore, to create an observable, you need to take a linear combination of the Pauli spin matrices with 3 coefficients, B1, B2, B3. Those are the 3 components of the magnetic field. That is how the magnetic field acts upon the state space. So in other words, given the value of the magnetic field, that gives you the coefficients. Then you take those coefficients and you combine them with the Pauli spin matrices, And that gives you an operator, which is which is able to act on the states. So it's exactly in that way that the magnetic field acts on the state space. It acts through the Pauli spin matrices. The Pauli spin matrices are giving you, it's giving you. I mean, the reason it'll become clear later on because we're talking about representations. But the basic idea is that the photon, which is the carrier of the electromagnetic force, that thing is a vector. It's a spin 1 particle, but the electron is spin 2. So you need some way of going from spin 1 to spin 2, right? In order for the electron to be influenced by light, you need you need for something with spin 1 to affect something with spin 1/2. And so there needs to be something that binds them together. And that thing that binds them together is exactly the representation, the coupling between the spin 1/2 and the spin 1 representation, which we're about to learn. So that's what you would use. That's what you would use in that case. So really, it all depends on which system you're going to use for the C2. And what they're trying to use in real life is something that's way more complicated than that. They're trying to use, like, some people are trying to use nuclei, atomic nuclei, and the state of an atomic nucleus. So they're trying to use very cold atomic nuclei. They have a quantum state, and if you keep it very cold, then maybe the light won't come in and screw up the state, or maybe it's really good to have that mass gap. That way, if you have low-level radiation, it won't screw up your quantum state because it can't interact. It can't dump its energy into the state. So that's typically why these people who are doing it, they need to work cold, and they need to use strong magnets, or they need to use optics or something like that. It's pretty simple. I mean, they just keep it, they try to keep it very, they try to make it seem so complicated, but really it's all they're doing. They're literally doing linear algebra on a table. Okay, see you later.
Bye. Thank you.
Hey,
oh, hi. I didn't see that there's someone else. Okay.
No worries. It's just a very quick thing.
Yeah.
I just wanted to let you know I sent you an email about the assignment.
What is it about? Let's see. Oh, I didn't get your email. Where did you send me the email?
Here, let me double check.
Let me check my spam. I see. I see it. Where did this thing go? I see it now.
Yeah.
26 February. Oh, but you just sent it now, didn't you? Oh, let me see.
No, earlier today, I think. 10 is when I have it sent.
Yeah, I mean, usually I don't, there's no, it's like it's not really appropriate because it's like unfair really just to do that. But I mean, when is it due? It's due today, right?
Yeah.
Why don't you just go to sleep for a couple of hours and try to work on it tonight? I don't know. It's not. I wish people wouldn't ask that because it's like.
I understand. I also wish I didn't ask because.
I mean, usually I just say no for everything.
Enough time. It's been the past 3 days. It's been. I don't know why.
Are you a grad student or a undergrad?
Grad student.
Yeah. Okay. So I don't. Let me deal with this 1 second.